me to introduce myself?
Yes.
Well, I'm Greg Abram. I'm with the Visualization Group at the Texas Advanced Computing Center. I want to tell you a little bit about what we do here in the Viz Lab. The basic idea here is that scientists come into TACC to use our computers to do big science. And what they do is they simulate physical systems. So what their simulations produce is huge bodies of numbers. And sometimes they can do statistics on those in order to understand what their science is producing. But often they really need to generate pictures that represent the data that the simulations produce. And my group's specialty is to take their simulation data and to create imagery from it that conveys the information from the simulation. So what you see here are a bunch of the different things that we've done here, just as an example. Up here on the top, we have a group of people who are interested in modeling the physical structure of the Earth. So they visualize earthquakes that really happen, and by comparing the results of their simulation to what the earthquake actually did, they're able to decide that their simulation is representative of what's really going on. Down here we have data from the Los Alamos National Lab. They're very interested in climate modeling, and this is a visualization that shows that their ocean model and their atmospheric model cooperate well. And you can see the little spiraling storms there, and as they're dragging heat across the ocean. So you see their trail as heat in the ocean. Other groups that are interested in studying what happens if an asteroid strikes the Earth. So they have modeled a 250-meter asteroid striking the ocean off of Seattle to ask the question, is this going to cause a tsunami? Turns out that the forces in the ocean are destructive rather than constructive. So if a perfectly round 250-meter asteroid strikes the ocean at precisely 45 degrees, it's pretty clear that it's not going to cause tsunamis. Surprising them was the amount of water vapor that gets into the stratosphere, because water vapor is a greenhouse gas, and that would be a major problem. But basically, our role in life is to develop ways for scientists to look at their data using visual imagery and to understand their science as well as they can, and also, for that matter, to convey their science and communicate it to the world at large. People can build these models that model physical systems, but it's very difficult for them to understand what those models actually represent. I mean, the models themselves don't create pictures. The models create huge numbers of numbers. And while they can sometimes do statistics on those numbers in order to understand something about what's going on in them, they understand much better if they are able to look at the image, the data in various ways, that just takes advantage of our ability to look at things and understand them. We've evolved for billions of years, and we have developed incredible abilities to look at imagery and see patterns and see things that we don't expect to see and surprises. And it's a very, very useful way of gaining bandwidth from a computer into a human mind. Often scientists want to understand physical systems that happen where they can't observe it. We can simulate an asteroid without actually having to have a 250-meter asteroid strike the Earth. We can look underneath the ice shelves of Antarctica so that we can understand the flow of warm water from the Southern Ocean, underneath hundreds of meters of solid ice. So very often simulations take place in areas that you can't directly look at. We can also simulate, for example, galaxy formation in the early universe, where there's nobody there that can actually look at it. We can simulate it instead and try to understand some of how the galaxy originally formed. So that's it. We simulate when we can't directly sample or directly observe processes. And once we've done the simulation, we need to create imagery from it that looks like something that's accessible to a normal human being, rather than boatloads of numbers. For me, the biggest challenge is that simulations that are large enough to have to run on TACC supercomputers produce very, very large amounts of information. And the problem really becomes, how do you produce images from enormous data sets that are so large that they have to be actually represented on, use supercomputers to do any kind of processing to them at all. So supercomputers are odd things to program. There's a lot of challenges that are involved in dealing with data that has to be spread out all over a supercomputer rather than in one system that you're actually able to look at a desktop on. Past that, the question becomes how you combine lots and lots of different kinds of information in single frames. Typically, it's easy to show the temperature in this room as surfaces where the temperature takes on a solid value. But if you want to see complicated stuff like the interaction between many, many different particulates in the room, somehow you have to have many different degrees of freedom in the visualization you're looking at. And we're looking at sort of non-standard ways of doing that using techniques from the natural world, using natural shapes and natural colors to convey more information than in typical sort of cold visualization tools. The biggest excitement for me is that I get to use the knowledge and techniques that I've built up over many years to actually help scientists. And so it's fascinating to me to understand the science that is being presented in these visualizations and to come up with the most appropriate and effective ways of showing them off and develop new algorithms for generating the pictures and new color codings for things, all in the service of people who actually are doing the real science that moves the world ahead.